you dream of a classroom where learning is natural? Can we inspire students to lifelong learning? What exactly is the purpose of an education? Inspiring students to be curious, independent, creative, innovative, deep thinking, confident, proactive, collaborative, determined, educated. Rise to the challenge of changing the world. This is teaching. This is learning. This is who we are. Welcome to the Tabletop Inventing Podcast.
Could recent research be a breakthrough in Alzheimer's treatment? Is science more than equations and logical pursuits? Could it actually be that science is more about creativity than logic? Listen in to today's podcast for the surprising answers. Hey there, Innovation Nation. I am thoroughly enjoying the start of springtime here in the high desert. The flowers are blooming and our little orchard out back is beginning to come to life. I love seeing the flowers and trees growing and getting ready to bust out in a cacophony of color and excitement. It reminds me of the growth and excitement we experience every summer in the Inventor's Bootcamps. I get really excited about the Inventor's Bootcamp because there's so much growth and creativity and excitement as the students build crazy engineering contraptions with 3D printers and wire them up with a little electronic trickery and programming prowess. The amount of creativity, confidence, curiosity, and deep thinking of the students in these summer camps is almost unbelievable. To find out more, visit www.ttinvent.com/bootcamp now. That's www.ttinvent.com/bootcampnow. Or you can just visit the ttinvent.com website and click on the Inventors Bootcamp button. Today's interview may bring some surprises. My discussion with Chris Schaffer, a professor at Cornell University, unearths some common myths and dusts off the truth about science. The perspectives in today's podcast are not for the faint of heart, so prepare for a massive unveiling. So my guest today is Chris Schaffer from Cornell University. Chris is a faculty in the biomedical engineering department at Cornell University, and he describes his research as about 1/3 novel optics-based methods for biomedical research and about 2/3 the study of cell-cell interactions in the brain, particularly pathologies. He is broadly interested in science policy, and he spent some time in the office of Ed Markey, and we'll ask him a few questions about that. And he's also got some very interesting ideas on educational innovations, particularly science as a creative process for discovery. So Chris, tell us a little more about yourself.
So like you say, I run a lab in the biomedical engineering department at Cornell University, where we spend some of our time developing new optics-based tools and techniques for biomedical research, mostly tools and techniques that would allow us to directly visualize the behavior and the function and the arrangement of cells in animal models, like in rats and mice. And then we give these animals diseases that we would like to have a better understanding of the cell-cell interactions that cause the disease. For example, there's mice that have been genetically engineered to get Alzheimer's disease. And about 2/3 of our effort takes these animal models of diseases and the optical tools that we develop and tries to elucidate the interactions among different kinds of cells in the brain and other parts of the central nervous system that give rise to particular symptoms in a disease. I could give you one example. Right now we're working on a project to try to understand why brain blood flow is decreased in patients who have Alzheimer's disease. So Alzheimer's patients, they have about a 30% reduction in brain blood flow as compared to non-Alzheimer controls. And a 30% reduction in blood flow, that's a lot. That's like if you're laying down and you stand up too quickly and feel dizzy. That's about a 30% reduction.
Wow.
So Alzheimer patients basically walk around like that all the time. And this has been known for decades. But the mechanism that causes that decreased blood flow has not been clear. It's not your heart or the big blood vessels in the rest of your body. And it's not even the large blood vessels in the brain, at least until very late in the disease, they start to show some signs of pathology. But this blood flow decrease is a very early feature of the disease. And if you don't know what causes a symptom of the disease, it's very hard to identify a way to try to treat it or to cure it. So we used animal models of Alzheimer's disease, used high-resolution optical imaging to look at the vasculature in the brain of these mice. And what we discovered is that the problem isn't in the big blood vessels, but in the tiniest blood vessels in the brain, the individual capillaries. We found a small subset of capillaries, and the Alzheimer mice are plugged. They have something that's stuck in the vessel that's stalling blood flow. It's just a few percent of the vessels that are stalled, but in controls, in animals that don't have Alzheimer's disease, basically all the blood vessels, all the capillaries in the brain are flowing. So if a few percent are stalled, then the ones that are right downstream from that are going to flow very slowly, and the next branch downstream will be impacted a little bit. This few percent of capillary stalled adds up to a significant reduction in overall brain blood flow. And we've recently identified what causes these small stalls. It could have been, a small clot or a weird shape to the vessel or a narrowing or something like that. But it turns out it's white blood cells that are firmly adhered to the endothelial cells, the cells that line the blood vessels in the brain. And we've recently done experiments where we got rid of those plugs. And when we did that, the blood flow speed improved dramatically in these mice. So we're gearing up now for studies where we'll try to understand the downstream consequences of eliminating these capillary plugs. So does it improve the cognitive performance in the mice? Does it slow or change the development of the disease over time? And we'll be looking to try to understand the upstream molecular pathways that leads to this adhesion of leukocytes to try to identify places where you could potentially intervene therapeutically. We're very excited about this for a couple of reasons. One, if you could improve brain blood flow by 30% in Alzheimer patients, you could probably have a cognitive benefit from that right off the bat. So this is something that, if we're correct and if things move forward in a way where there's real therapeutic potential, this could immediately benefit Alzheimer patients. The other reason we're very excited about it, though, is, as you probably know, Alzheimer's disease is thought to be caused by aggregates of a small peptide in the brain called amyloid beta. Mm-hmm. That amyloid beta, it's produced by neurons, and it's dominantly cleared out of the brain through the vasculature. And single peptides or molecules of amyloid beta are not pathogenic. They're not damaging, but aggregates are. And you're going to get more aggregates if the concentration of amyloid beta is higher. So if amyloid beta is dominantly cleared out through the vasculature, and you have this capillary plugging phenomenon that's decreasing blood flow, that's sort of like plugging the drain. So the amyloid beta can't clear as well. If it can't clear as well, its concentration will be higher. If the concentration is higher, you get more aggregates. It's the aggregates that drive both neural death, which is one of the ways that you lose cognitive function in Alzheimer's disease, but the aggregates also drive inflammation, and we think it's that inflammation that leads to the leukocyte plugging. So this suggests a positive feedback mechanism in the disease, and anytime you find a positive feedback mechanism in the disease, it's time to break out the really good champagne. Because it suggests that if you blocked this on one or the other side, you could do more than just improve brain blood flow in Alzheimer patients. You could potentially delay onset or slow progression of the disease overall. So that's, sorry to go on so long, but that's sort of an example of the kind of work that we try to do here using optical tools to directly investigate the cell-cell interactions that drive specific symptoms of a neurological disease.
Now I have about 10 questions, but I can't ask them all. So I'll limit it down just a little bit. I have personal interest here. My grandmother had Alzheimer's, and it was really sad to watch that occur, that process.
Yeah, it's terrible. Both of my grandmothers have died from Alzheimer's disease, and I just, seeing that, you can't imagine a worse way to die.
Oh, yeah. And so as I was thinking through a little bit some of the things you were saying, one of the questions that popped into my mind is, since there are white blood cells involved, is this sort of an autoimmune response? Have you done any theorizing about upstream a little bit? Like, why is it doing that?
Yeah, so that's a great question. It's certainly an inflammatory response to the amyloid beta aggregates. I don't know that I would call it autoimmune in the sense that typically when people think of autoimmune disease, you're thinking about an immune response or an inflammatory response that's directed against an otherwise totally normal antigen, like having antibodies against DNA in lupus, for example. In this case, the aggregates of amyloid beta, they both specifically and indiscriminately bind a whole bunch of different receptors. Our collaborator down at Weill Cornell Medical College, Constantino Iadacola, has done a lot of work identifying what some of these things that amyloid beta aggregates bind to in order to drive inflammation. But they bind to some of what are often called scavenger receptors on a wide variety of different cells, and they activate inflammatory pathways that way.
So, and the next question I have is, because I'm not horribly familiar with this particular disease area, are there already medications or other things out there that might be able to make it easy to start thinking about like treating this, white blood cells adhering to a place where you don't really want them to adhere, or things like that?
Right. So right now for Alzheimer's disease, there's really no disease-modifying therapies that are out there. There's some ideas for approaches that try to block the aggregation of amyloid beta or to decrease the production of amyloid beta. And some of those are beginning to move forward into human clinical trials for familial forms of Alzheimer's disease. In terms of the blood flow issue we've identified here, I mean, already we have the capability to block this leukocyte adhesion, or block the white blood cell adhesion, which gets rid of the capillary stalls. But I don't really think that's going to be something that you'd want to move forward with in humans. So it's a great tool for us to be able to study things in mice, but you really don't want to prevent white blood cells from being able to stick to the wall of blood vessels and crawl into the tissue, because that's how your immune and inflammatory systems deal with things like bacterial infections, fungal infections, and cleaning up little wounds and things like that. So we really have a significant step in this project in front of us, where we're trying to delineate the molecular pathways that connect amyloid beta aggregates to the white blood cell adhesion. And we have some ideas and some hopes there, but at this point, we're just at the beginning stages. But that's a major research direction over the next couple of years, is to try to dissect that pathway as best we can, with the goal of trying to find places where you could intervene. Now, there are some things that suggest this could be a promising place for therapies. First is probably the cell that we would be most interested in affecting would be the endothelial cells that line the blood vessels, to get them to quit upregulating the proteins on their surface that the white blood cells stick to. So that's good news, because then that suggests we don't need a drug that can cross the blood-brain barrier. And that's been a challenge in many therapies for central nervous system diseases. As we've evolved over time, this very, very tight barrier that separates brain tissue from the blood, and therefore from the rest of the body, probably as a intrinsic defense mechanism. If your brain gets infected, then or has some problem because of exposure to a chemical or something, then everything shuts down. So we've evolved to protect the brain very well, but that also tends to keep therapeutics out of the brain and makes it harder to treat brain diseases. In this case, for this blood flow problem, we might be more interested in just treating the endothelial cells, where you wouldn't have that challenge in terms of a drug that has to cross the blood-brain barrier.
So now that you have step 2 and it sounds like a significant step 2, and
yes,
you're obviously going to be interested in getting funding for this, and this is a very nice segue into another question I have for you now, because I watched one of the talks that you gave about your experience in Washington. Why don't you tell our audience a little bit about what you observed about science and scientists in that perspective, and how we might be able to, inform educators or teachers a little better on how to prepare the appropriate response to sending scientists to Washington.
Yeah, so maybe a little background. So I was fortunate enough to win one of the what are called Congressional Science Policy Fellowships. This is a program that's been run for over 40 years by the American Association for the Advancement of Science. And this program places about 30 or so PhD-level scientists in individual offices in Congress, either a personal office in the House of Representatives or the Senate, or one of the committees in the House or the Senate. And these positions are funded by various scientific societies. Mine was funded by the Optical Society of America and SPIE. There's another, I should say, 270 or so of these fellowships where people go and work directly in federal agencies, like in the Department of Defense and Interior, Department of State, and Health and Human Services, and other places. So anyway, I won one of these fellowships, and I spent a year working for now Senator Ed Markey from Massachusetts. He was actually in the House of Representatives when I joined his office, and then successfully ran for the Massachusetts Senate seat when John Kerry moved to Secretary of State position. While I was down there, basically every scientist that came through to advocate for the period of a year came and talked to me. And at the beginning, I really enjoyed it, because it was like talking to my compatriots, other scientists who were down at Capitol Hill. But over time, I came to realize that scientists are actually probably the worst advocates for their own interests of any group that I think comes down to DC to lobby or advocate for things. Scientists make a number of, I think, pretty fundamental mistakes in advocating for what we need to fulfill our role in society. And if you'd like, I'd be happy to talk about a few of the things that I think scientists could do better when they come and talk to representatives on Capitol Hill and other policy positions.
Oh, by all means, I think our audience would very much like to know, how do we approach Washington in an intelligent way?
So one thing, scientists, we should be very proud of our peer review system, where we compete fiercely for scarce resources to try to best allocate the funds and other resources we have to do the best quality work. We don't want to turn peer review over to Congress. And yet I find lots of scientists who come in and lobby for or advocate for increased support in very narrow areas that are parochial to their own scientific research interests, and often even explicitly stating that could be at the expense of some other area of science. And I think when we, as scientists, go and try to talk about what we need to do our jobs in society, we really need to be advocating for, I guess, what I call capital S science, all of science. So it's fine to talk about the individual work you do and its potential impact as an example of the kind of things that funding science can do. But as we all know as professional scientists, important advances in one field are often built out of discoveries in another field. It's not possible to look forward and predict with any degree of realistic certainty which studies are going to have big impacts and which aren't. And so we really want sort of broad spectrum of support for science. And when you go in and advocate for one narrow area of science to someone whose job is not to sort of make the decision that we should invest in hematology, but not in some other discipline, it's actually damaging, because the view of the staffer or the member of Congress you talk to will be, scientists, you should get your act together and identify your priorities, and then come to us with these priorities and a reason for why you need resources to achieve them, and we're going to work with that. Don't come in and ask us to set your priorities. So that's one mistake.
I mean, just interjecting here a little bit. I mean, as scientists, it seems like we should be able to sit down and say, well, these are our top 3 priorities in optics. These are the things that we know are hard. We know that they're going to be game-changing technologies, and we think that if you fund in these areas, that'll be positive. I mean, do we not do stuff like that?
So there are some disciplines that are quite good at doing that. For example, astronomy as a discipline sort of conducts field-wide surveys and focus groups, things like that, to try to develop what the field as a whole feels are the top priorities for advancing research. And then those are put forward in reports, and those reports are then used by other scientists in funding agencies who are making the decisions about allocation of resources in one place or another. And those reports are used to try to guide development. But that's certainly not, I would say, the standard across most scientific fields. But it would be a good move where individual disciplines work to identify their priorities. And then, of course, there has to be decisions that are made, about allocations between disciplines as well. We have a great system for doing that, where professional scientists serve as program officers and program directors and things like that in major funding agencies like the National Institute of Health and National Science Foundation. And the job of those individuals is not just to push the paperwork associated with reviewing and funding or declining individual grants, but also to sort of keep their fingers on the pulse of their community. And try to pick out what are the areas of science that are most in need of investment. But another thing that I have to say that scientists do that or often do when coming to DC is they're a quite whiny group. So the typical discussion revolves around the difficulty in securing federal funds, given the very low funding rates in most federal funding agencies right now. The uncertain career prospects for young scientists, much of that resulting from kind of unpredictable and relatively low funding levels that we have right now. It is true that these are problems that make it harder for scientists to make progress, but that's not why we fund science. Science isn't funded as sort of a welfare program for people who have relatively high salaries, whose job it is to go do the things that they think are interesting and they're curious about. Like, that's not why we fund science. We fund science because of the potential for big positive impacts on the rest of society. And there are problems that we're facing going forward as a society that we are going to need science and technology, innovation, and solutions to contribute to solving the problem. Developing a sustainable relationship between our societies, our climate, and energy production. Continuing to decrease the burden of disease around the world. Continuing to drive economic development that lifts people out of poverty and gives everyone, or gives a broader swath of the population a chance at a life that has some time for recreation and opportunities to contribute broadly to their society. So these are the things that science could do if it had good support. And there's reasons to think that science can help to solve some of those problems because so many have been solved in the past through science. For example, right now, we live the historical equivalent of 2 lives. 200 years ago, Steve, you and I would be dead. And many of the people listening to this podcast would be decidedly middle-aged. But now we have the functional equivalent of 2 lives. And that's due to science and technology innovations, much of it in sanitation and agriculture, but also in biology and medicine and vaccinations, for example. So that's an enormous accomplishment that's had a profound impact on our society and around the world that was achieved through science and technology. Another example, the growth in the per capita gross domestic product in the United States from World War II to today. About 50% of that growth is directly attributable to science and technology innovation. Only a small fraction, I think it's around 20%, is new natural resource extraction. And much of the rest is improved education and increased lifespan, which is much of it secondarily due to science and technology innovation. So if you look at that, that represents the greatest creation of wealth by a minority of a society, scientists and engineers, for the rest of the society, for everyone. In the history of humanity. So this is the best we've been able to figure out how to do in terms of strategies or things that we can do as a society to give everybody more free time, give everybody opportunity to have ways they can live fulfilling lives, contribute to their neighbors and the rest of society. This is the best we've been able to do. So these are the arguments that scientists should be making when they come to advocate for more resources. The argument should be, there's big problems in society. Science is one way that we could address these problems. And now we could talk about what it is that science needs as an enterprise to be able to fulfill those promises in society. And that's where the discussion of funding and immigration reform for individuals that are in higher degrees here and improving career prospects for young scientists, that's when we would want to start talking about those things rather than talking about those as the reason that we need to fund science.
Excellent. Well, thank you for giving us that perspective. As being in the field for a while and hearing a lot of the things that I've heard from other professors, it doesn't surprise me that they would say the same things when they went to Washington.
Right, exactly.
So I'd like to take a left-hand turn here and ask you a little bit about your philosophy of education, because you've certainly had an opportunity to think through the research process and see science from the top down. Tell us a little bit about what you think about things we can do in education to improve the interest in science and the excitement, I guess.
I mean, I think the main thing, if you ask, most people sort of what they think of as science, they often think of it as sort of an assembly of facts and ideas. And that's not what scientists think of science as. Those facts and ideas, that's sort of science history or science reference. Science is a creative process for discovery that's often collaborative, sometimes competitive, sometimes frustrating, sometimes exhilarating, but very sort of human process, but it's a creative process for discovery. But we don't teach science that way. We often teach it as a collection of static facts that people have, discovered over the ages, and they're written down in books. But we don't have to. It's possible to teach science as a creative process for discovery at all levels. So, for example, you could imagine a series of experiments that are as open-ended as possible and as guided as necessary, so that students discover Newton's 3 laws of motion for themselves. And then after that, they learn about the old dead white guy and the apple and F equals ma and the other formulas. So this would be a way for students to experience the thrill of discovery, to gain to peek behind the curtain and understand what it means for something to be a piece of scientific information, what that means in terms of the degree of rigor and vetting and review and cross-checking that and controls and things like that that are done to produce what we would call a scientific finding or a scientific fact or a scientific theory. And I also think it could help people to imagine themselves as a scientist a little bit. And that could open the door to a really exciting career for some people. But then even for people who don't become scientists, I don't think anyone is going to be able to make it through a life in modern society without having to make really critical decisions that depend on having to interpret, at least at a high level, science and technology information. We're all going to be faced with health decisions. When we go to the voting booth, how should we weigh a candidate's views on climate change and energy policy? Should we vaccinate our children? And how do we look at the information coming from scientists and information coming from other sources and vet that in a way where you could make a decision that is really, in your own best interest?
So as a scientist, I mean, you and I, we're obviously biased about this, but could you articulate for our audience kind of the central thinking processes that a scientist goes through that will help people make those kinds of intelligent decisions?
And one thing I would like to say at the outset, I don't mean to imply that scientific information is the only kind of information that's important in making a decision, either as an individual or in setting policy. There's other kinds of information that are also important: tradition and religious beliefs, gut feelings. Like, all of these are also important pieces of information that we use a lot when we're making decisions as individuals and as a society. But I would say that because of the way it's generated and vetted, scientific information maybe deserves a privileged place at the table. And the thing that makes scientific information unique is that it's always tentative, it's always subject to revision, it's always being criticized, looked at a different way, and pieces of or ideas or concepts that emerge from this sort of very critical, rigorous, always questioning kind of approach, and they stand the test of time. They remain still standing after many assaults. There's a really high degree of certainty that that kind of information is correct. And that's different than other kinds of information where there's not this sort of sense that we're going to go back and revise it, and we're going to go back and look at it a different way, or when a new result comes in, we'll interpret what that meant in a different way. So it's just the fact that we don't take things at face value. We're always questioning. We're always not just questioning other people's work, but our own work. And we put this information out in a way, peer-reviewed publications, where it's out for all other scientists to look at and able to try to repeat experiments, to try to do other experiments that would support or refute the ideas. So everything we did, how we did it, and what the data is are made available for open critique. And that's a different approach to information than, I guess, what you would see in many of the other kinds of information that are important, but don't have the same kind of rigor.
Well, I think a lot of people probably come look at science from the outside. And, we get this quintessential view when someone says science, the first thing that pops into someone's head is Dexter's Lab, the cartoon, or some scene from a movie with a guy with a bubbling potion in a beaker or something.
Right.
And as scientists, we would look at that much, much differently. We basically look at life and think, if we tinkered with it a little this way, or if we just twisted it a little that way, I wonder what it would do. And we tend to look at things and ask, well, what is the one case in which it might fail?
That's right.
If we tinker with it just like a way you wouldn't think about it, if we just poked it on this side, would it fall apart? And what you're saying is that kind of curious, tentative approach to information, to decision making, might help us find better choices sometimes, or better ideas.
Absolutely.
So I wanted to back up a little bit and ask you a question, because you talked about science as a creative process, and we don't normally think of science as a creative process. We often think of it as a logical process, but as scientists, we kind of know this deep down that it is a creative process. So let me ask you a personal question. What sort of creative outlets do you have outside of science?
interestingly, I've learned how to, I've done a bit of metal sculpture, mostly through blacksmithing. And I became very interested in that as a postdoc and have made quite a few pieces, mostly sort of architectural things, things around the house and that kind of stuff, but some more artistic as well. And I think you commonly find in scientists people who have other artistic and creative outlets, frequently find musicians and writers among the scientific population. But, it is a very creative process. It's just a creative process that's tempered by experiments. So, when you're great quotes, people talk about the difference between insanity and genius can be just a very thin line. And often there is this feeling about that. So in science, what we're essentially doing, we're working at the very boundary of human knowledge, at the very edge of what's known collectively as a species. And we're trying to look past that and understand what else is out there. So we're looking past what's known and trying to make predictions and sometimes just a guess, sometimes going on gut instinct, but making a prediction about what's out there. But then we go and that's the creative part, trying to see past what current knowledge is to what might be the truth, or what might be the next piece of information that we could acquire. But then we go and we rigorously test that idea. There's sort of a creative phase of coming up with a hypothesis, with an idea, with a research direction. And then there's this sort of very rigorous, and as you described, logical phase where systematically testing those ideas through carefully controlled experiments, evaluated by our peers, in order to see whether or not those creative ideas are right. And I think that's what distinguishes the creative aspects of science from, say, creative aspects in other disciplines. We do have this check. In the end, the things that we come up with, we have to confirm them to be right before there's something that we tell the rest of the world about.
Well, we don't often get that perspective on science as a creative process, and I like it that you talked about it as a creative process that's tempered by experiments, because that's exactly what I do. We just don't verbalize that as much, and maybe we'd be more effective in Washington if we verbalize some of these things a little more. Anyway.
Yeah, I completely. In fact, I think one thing that's very important to explain is how the science works as an enterprise, both to policymakers and to the public generally. I don't think we would find anyone who would say that it's not worth a $1 billion investment in a research program that was guaranteed to cure Alzheimer's disease. I don't think we'd find anyone who would say that that's not a worthwhile thing for say, federal tax dollars to be invested in. But we just can't do that. It's not the way science works as an enterprise. We're working right at the edge of knowledge. It's always hesitant. It's always uncertain. It's always slow. There's often things that emerge in other disciplines which have a huge influence in places that was unexpected. And the best way we've been able to figure out how to move forward is to make broad-based investments across many different disciplines in science, and to have scientists try to, through our peer review system, vet which things are of the highest merit and most worthy of support. But I think we need to help explain how our enterprise works collectively, how science works as an enterprise, so that people better understand why things are slow, why the research dollars are invested so broadly, things like that.
Excellent. Well, as we wrap things up here, I do want to get to our two questions that we always ask. And the first one is, in this digital age with YouTube and Facebook and Wikipedia, where we can just go out and Google just about anything, what does it mean to be, quote, educated?
Yeah, so from my perspective, and we see this even as a professional scientist, there's been a significant shift. It used to be being educated meant being the one who had ready access to a lot of ideas and theories and concepts and facts. But increasingly, now we all have access to an overwhelming amount of information and concepts and facts and theories. And so being educated a lot of it is being able to vet the quality of information that's available to you, and maybe more importantly, understanding how to make use of that information and doing something productive, either making a decision or creating a new product or dreaming up the next scientific hypothesis. So instead of just knowing things, it's more about being able to evaluate the quality of different kinds of information, theory, of ideas, and being able to use them to do something productive. And again, I think there's a need to shift emphasis in our educational systems to emphasize the new things that an educated person needs to be able to do, as opposed to just remembering lots of things. So teaching and learning strategies like project-based learning, where students are presented with instead of being presented with a lot of background and then later there's an application, they start right out with, here's the problem, you have to figure out how to solve it. And you need to go and find the information and the ideas that you need to solve the problem, and you need to vet the quality, and then you need to apply them to solving the problem. So this is a sort of an alternative way of educating, as opposed to, a faculty member or a teacher standing in front of a classroom and lecturing for an hour. It's more presenting a problem and then helping to mentor and facilitate students in developing their own solutions to it through their own search for information and their own vetting and their own application of it.
Excellent. Well, you're definitely speaking our language there when you talk about project-based learning. I'm a big fan of that in what we do. So let's wrap this up with, and I'm going to phrase this a little differently because of your recent experience. If you had an opportunity to articulate to Congress or to an investigative panel in the Senate, what would you tell them about the purpose of an education in our current society?
Yeah, so an education is always going to be playing, many roles in an individual's life. Certainly, one purpose of an education is to help individuals be able to make the best decisions for them personally. As I mentioned earlier, decisions about their own healthcare or who they should vote for and things like that. So helping people to be able to make better decisions in their own life. At a broader level, having a very educated workforce and an educated society gives an opportunity for the kinds of innovations in science and technology and business and art that help lift us all up collectively by increasing the amount of dollars that are around that can be used to feed people, to entertain ourselves, and in increasing the amount of free time or leisure time that we all have to be able to find aspects of our lives that we enjoy, and increasing the opportunity for us to be able to do something that doesn't just help ourselves, but that helps others around us as well. So it seems that in the modern world, most of the things that have big impacts like that are things that come from solid grounding in classic academic education. And I do think that there's an important for a very broad education. I'm at Cornell University, one of the Ivy League universities, and it prides itself, even in colleges like mine, the College of Engineering, on providing a broad liberal arts education, a broad understanding of history, of different cultures, of sociology and psychology. And I think that broad liberal arts education helps you become someone who can be adaptable and better able to shift and change as times change and as society changes.
Thank you so much, Chris, for sharing your insights and your experiences. We have definitely, I have certainly enjoyed it as a scientist. It's very validating to hear you say some of the things that I've suspected for a long time, but I didn't necessarily get that perspective coming through the system, even though I was inside the system. It seems like some of these things should have maybe been more obvious to me, but like you said, we very often don't see these things maybe until we get to a PhD level investigation. So thank you so much for sharing that.
And Steve, thank you so much for having me. I definitely enjoy talking.
All right. If any of our audience wants to get a hold of you, what's the best way for them to do that?
They can send me an email. My email address is CS, as in Charlie Sam. So it's CS number 385 at cornell.edu.
Thank you so much, Chris. Our audience has certainly enjoyed that, and I appreciate you taking time today.
Great. Thank you very much.
If you've been enjoying the conversations and insights here on the podcast, share it with a friend. Great ideas demand to be shared. You can also help fellow parents and educators by subscribing to the Tabletop Inventing podcast in iTunes, leaving a rating, and writing a review. If you use Android, subscribe, leave us a rating, and write a review in Stitcher. Links to subscribe can be found at www.ttinvent.com/podcast. Contact us, and we'll think through the comments and answer your questions here in the podcast. And be sure to let us know if you'd like a shout-out or to remain anonymous. You can share your comments and questions at www.ttinvent.com/podcast or by emailing us at podcast@ttinvent.com. Let's discuss your thoughts and questions. Join us again next time when we will again seek to answer the question, what is the purpose of an education? And as educators, how do we awaken the inventor in each of our students?